Okay, so hello everyone. Welcome back to the 10th section for the series of video tutorial. And in the previous two sections, what we've done is we look at the a simulation of a system mechanism for both the deployment and also the load carrying behaviors in these mechanisms. And we start using a new element, which is this particular 3-point rotational spring element. And in this section, what we hope to do is to briefly show you how we are able to derive these 3-point rotational spring elements. And one of the other goal that we hope to show you here is that when you go into the derivation, you would soon realize that the method we're going to be using, the central difference, looks just like exactly the section 5. So we're almost like copy pasting the code we've been using in section 5 and to apply that central difference process into the 3-point rotational springs. And that's just want to show you how versatile these methods really are. And without further delay, let's get started. So these 3-point rotational springs defines, um, in order to define that, we need to calculate the angle between basically two vectors formed by the three node, right? So looking at it, let's get started with three node. And these three nodes are xi, all 3 by 1 vectors, xj, and then xk. So along this bar here, or along this line here, there's going to be a vector v1, and we can define it as xi minus xj, right? That's how we find this vector. And again, from xk and xj, we can define the v2 vector. So this actually gives us a way of finding the folding angle in between so basically the folding angle formed here by these three nodes that we're seeing in the 3D space. So the particular angle here, theta, or let me actually use the same notation I'm using in the note, which is the phi angle here. The way we can find it is basically using the cosine rule, right? So we know that the cosine of this phi angle is basically the dot product of these directional vectors. So we want to make it a unit vector for the v1 and also for the v2 here. And that is basically a dot product between the two, right? So a vector divided by its length. So this double line, double bar here represents the norm. So that's basically how we calculate the length of a vector. And after getting a dot product, that gives us the cosine of the theta. So this is the trigonometry we've been learning since, I don't know, junior high school or senior high school. So hopefully this is not something, this is something very easy, right? And after that, to find the phi angle, we just take basically arc cosine of these entire value on the right, and on the up is v1 dot product v2, and then on the bottom is v1 times v2. So this is already when you, oops. Uh, yeah, yeah, when you're dealing with so this is already just a number, it's not a vector after you take the norm, so we can write it like these. All right, so this is the equation we use to find the angle between three node, and we can quickly verify that using this particular example. And this particular function here basically just implement the calculation we just showed you on the screen. And this three node looks like we're going to be looking at the XZ plane. Z plane, it's X. The first node is 1, 0, 0, so that's here. XJ would be at here. That's I. and the kth node is here, 1 unit in the z direction, and apparently the angle should be a right angle, so it's 90 degree. And if we use this find angle algorithm, what we found is that we get the theta of 1.57, which is in pi, so 1. Half a pi, so 0.5 pi. And so just pay attention here that we're not doing degree, we're using the rad unit, radius unit. So 1.7 rad is exactly 90 degree, and that's a good indication that we're doing the calculation right. So now that we have a way of calculating the angles between formed with the three nodes, what we hope to do is to create a potential, a spring potential out of it. So the system we're going to be looking at is really just like this, clips. So basically it has a rest angle is basically if you don't put any force there, where the system want to rest. So for instance, if I don't apply any force, these clips want to stay in this configuration, right? The angle between these two tips are forming an acute angle like that. And if I apply forces, it can deform, but I do need to, do a little bit of work to put some forces there to open it. So that's the same thing this three-node rotational spring can do. So let's assume that the red is its original configuration, right? So then we're going to have a phi naught, and then we can follow the convention using the large uppercase for undeformed configuration and the lowercase for the deformed configuration, which is a quite widely used notation. So again, IJK. So that's the undeformed configuration. That's the deformed configuration, right? If this is the phi naught, that's the original angle, the angle where there's no forces, where the system wants to stay at. Now we've opened this angle up a little bit from phi naught to phi. Naturally, this system will want to close itself towards phi naught by generating these two forces about the x on the xi node and the xk node, and then it's also going to generate another force here just to help maintain the balance to satisfy the equilibrium. So these are, shouldn't be writing phi. This should be f for closing, fc vector for closing. And this f at j is for balancing and making sure that everything is in equilibrium. That's the three forces it would generate. All right, so then of course, without making our life too complicated, we want to start with the simplest potential formulation, right? And the simplest of it would be linear elastic spring element. So basically, there's going to be a spring constant, 1/2 spring constant times the difference between the new angle and the stress-free angle. So that's pretty much the simplest formulation we can set up for these 3-point rotational spring, right? And as a matter of fact, this thing is so easy to code. We only need just 2 lines of code to create this function. So first of all, you find so this basically solves the full potential using this equation between the three node. It takes in the xi, xj, and xk node. It finds a theta value, and then it's going to be 1/2 times spring constant times theta minus theta naught square root. And that will give us the total potential of the system. So very easy, right? So after that, we already have the potential. What we need to do is to really just copy paste the code we have from section 5 for doing the central difference, right? So I pretty much did the same thing. But then there's something a little bit unique here because now instead of having just 2 nodes, we do have the third node, right? So we need to tweak the code a little bit, but overall it's the same process. So to find the force vector, we need to solve for the Jacobian of this potential. So that's done by calculating the nabla x of these potential of spring. So this is the notation we're going to be using. And basically, it's going to be a 9 by 1 vector here for that Jacobian of the potential. The first term is the partial derivatives of u spring about the xi direction. Second will be yi, third will be zi. So the first three indexes are related to the node I in the three xyz direction. The second three indexes would be related to node j, so that's why this is xj, yj, and zj. And the final three would be xk, yk, and zk. That's for the third node k. And the central difference equation is exactly the same if you, let me actually bring this up, and I hope to show you a short comparison of the two. You will see that for this particular case, for the three-node spring, we just have three more um, variables or directions there for the central difference to happen, right? The equation is exactly the same. You take a step along the selected direction, and then you take a step backward in the selected direction. You find the potential, you calculate their difference, and then you divide it by 2 delta, which is your step length in the forward and the backward direction. So we keep doing these over and over for all these 9 directions, and after that we find our forces. So when it comes to the code for the forces, everything is the same, right? Except that this time, oops, on the left side, I have the 3-node rotational spring. On the right side, I have the 2-node bar. So the forces on the left is 9 by 1 because we have an extra node. And when we're doing the calculation, we just copy paste one of these to here to make it xk because that's the third node we need to do, right? And then we shift and pretty much that's it. That's the only difference. We change that to the accord like the a proper location, of course, right? For these because this all of this is going to be xk instead of xj or xi in the first two nodes. But you can see that for the calculation of xi and xj, the left code and the right code are identical. So for the first 6 index in the formulation, in the calculation of central difference, working on the spring is no different than working with the bar, although technically they're dramatically different element, but the derivation follows the exact same formula. So that's one of the nice things. So the next thing we hope to do a little bit is to just um, start working on a little bit of playing around with the to visualize the internal forces and try to understand what's going on there. Right, so this is the code we use to basically plot the forces acting on the 3-node as we change the current folding angle as well as the stress-free angle in the 3-node. So stress-free angle is here, current angle is this one, and we use the Quiver 3 to plot the forces. And we use the plots. So not Quiver 3, Quiver. This is 2D right now. And we use the plot to plot those line segments. So let's play around with it to visualize what's happening. So first of all, if my theta naught is the same as my theta, there should be no forces generated. And that's exactly the case, right? My theta naught is, oh, I think this one should be theta for better display, right? That's theta. Yes, this time the displays will match up. And if my theta naught is smaller than that, uh, then these forces will be generated trying to close up these angle from 0.8 pi to 0.5 pi, right? So this is what's happening here. So let's say if I now fold to a right angle, come on, generate something. oops, generate something. All right. So let's say I now create these right angle in here, but my stress-free angle is zero point 0.5 pi, which is basically at the right angle. These new forces now will try to, open up this angle so that I get back to the 90-degree location. So this is exactly what we should see in an actual 3-point rotational spring, just like the paper clips, right? If you apply forces, you can open it up, but once you remove it, when this thing should always try to go back to the stress-free angle, which is defined by the theta naught. Okay, I think I have not yet added my source code. Yes, I will need that. So add the source code to the pass, and now we'll get that little warning away. Okay, so this is how the force computations are done, and as you can see, nothing is very different. And the next thing we're going to be doing is to go into the stiffness, right? So remember that when we're talking about the Newton-Raphson method, we need both the internal forces and also the stiffness. And this time, the stiffness still is going to be that Hessian matrix because we have additional node. It would be a 9 by 9 matrix. And typically, we would prefer to use this matrix representation. So each one of these would be a 3 by 3 matrix, sub-stiffness matrix. That's a very easy way to organize the calculation, especially if we want to solve this analytically. And so for each of these matrix in the first this big 9 by 9 matrix, it's taking out one of the index there. This is still a 3 by 3 matrix, so that's basically what's been demonstrated here. So if you go into some of the related works where people do solve the things analytically, so for instance the Liu and Polino paper on how to simulate origami, in that paper, we'll see this type of representation being used extensively. So I guess this is one place where we can start getting used to it. But at the end of the day, what we need to do is just like what we've been doing in the section of 5. So let me actually bring that up again. So the right-hand side is section of 5. So for this particular matrix here, you can also break that into a 2 by 2 of 3 by 3 matrices. So see these as one matrix and use this index will make that happen. So that's just some of the things, some of the math notation we can do. But going back to here, what we've been doing in the section 5 is to actually just use the exact same formulas we have in the previous force equation, make a little tweak there, and use that to directly calculate the stiffness. So for each of the column, we're still going to be doing a central difference for each of the column, and it's just going to be done but for all the vectors, all the elements in that vectors at once. But apart from that, everything is still the same, right? So this is what we did in section 5, and we're going to do the same thing here for these 3-node rotational spring. Nothing actually changes, actually, you can see. So we've pretty much copy pasted the entire code from right to the left and adding these additional calculation for the xk, so the additional dimension there. So now the stiffness, local stiffness matrix for the 3-node rotational spring is 9 by 9. So we have 3 dimension more than what we have for bars. The xi and xj is exactly the same, as you can just briefly compare the result xi, right? This is just like the exact same code that we did. So the only new thing here is the xk, the add additional code for the xk. But at the end of the day, we go through the exact same assembly process to put together the final K matrix and we get our result. So nothing too crazy. And with that, let's actually try to compare the result between what we just did here with the stock element we have at this particular package. So I think this one is theta. So let me change that to theta. So that's yep, that's better. So when my theta not does not match, there's going to be forces generated. So the force we just created using the using this code is identical to what we have in the stock function. We just we value we this is needed because that indicate that we did the calculation right. And the stiffness, if you compare them, it's also identical, right? So they're basically showing the same result. So now if I change everything to 1 and 1, my force is 0. That's expected because if my current angle is matching the stress-free angle, there shall be no forces developed. But still, my system should have some sort of a stiffness because the spring is still there. Even if you move a little bit, you still need to see some forces. That's what that stiffness means. So, and also the stiffness we get from this code also matches that from the stock function very, very well. So this is nice. So we've done our calculation right. That's basically what's been demonstrated in these straight comparison with the CD element rotational spring, three-node rotational spring we used in the previous section for the modeling of the scissor mechanism. So, all right, after you see this code, I really hope that you just pause there for a little bit and just really stare at these, compare the section 10 code to the ones that we got in the section 5 code, and you will see that the only thing that's different is the dimension, right? That's really the nice thing about central difference. So once you come up with some sort of a potential of your system, you pretty much can copy paste code and just use central difference to find their internal force vector and the stiffness matrix. And the only little tweak you need to make is to change the dimension, make sure that you're capturing all the nodes that you need when deriving the total potential. So we'll keep seeing these show up in our future code because there's going to be, I would say, at least two more elements that will be derived using central difference, including a triangle and another four-node rotational spring element for origami systems. So they all can be derived with just the same mathematical formwork and very similar code, and that's one of the nice thing about it. So if you change the potential, of course, you would be able to tune these system from a linear elastic to any sort of a hyperelastic system you can capture using these. It doesn't need to be linear. So you do have the capability of going to nonlinearity and nonlinear material responses like the Octa model or some of the other hyperelastic model you might want to use for certain materials in your own simulation. So that's one of the things I hope to comment on. And the other thing is that in the previous two examples, we've demonstrated the simulation of a scissor mechanism, 2D mechanisms, and there's more applications for these three-node rotational springs. So I would like to show you one which is actually quite cool. So people recently are quite curious about the mechanical behaviors in the weaves and knit structures. So this is a yarn level simulation of woven fabric. So you can imagine why people are curious about it because, for instance, if you want to develop good bulletproof jacket for police officers, you want to use good fibers and then you want to make sure that the fibers are woven or knit together in a good way. you probably will want to run some sort of YUM level analysis. So they have this pretty cool model that has this three-node rotational spring, and they put together these to capture that the weave, the woven fabric system, and they use that to simulate a lot of pretty cool behaviors regarding the weave system. So this is actually a pretty recent paper, and that's kind of quite cool, honestly. So that just gives you one idea of where you can apply this type of things. And when it comes to the related classes, I think the most related class is still probably numerical method and finite elements methods. So numerical method, maybe from the math department, some of the undergraduate math department, you definitely cover central difference. And finite element class will give you an idea of how, different elements are put together. So it does not use central difference, honestly. Finite element, the way I understand it, is actually a math method for PDE. So people often treat what I showed you here, lumped parameter models, as some sort of finite element because there is elements in it, but well, mathematically they're quite different, honestly. So finite element is a if you look into the math details, it actually has a pretty specific math structure in terms of how it handles the PDE. So we aren't actually doing that, but I guess since we're using elements, if that helps you to understand, I'm okay with natural languages, which with any sort of name you want to call it. I'm pretty fine. I'm pretty open to that. But anyway, hope that at some point you will get to understand this little nuances between them. So that's all I hope to cover for these theory sections. And next time when we come back, I do hope to start discussing another example section again, and this time will be something very exciting. So origami and barn hinge model. So that's gonna be an exciting topic. So with that, let me end this particular video. And as always, wish you all have a great rest of your day.